Hello everyone and welcome to my presentation. My name is Songheng Zhang and I'm from Professor Wang's research group at Singapore Management University. Today I'm excited to share with you our work titled Don't Pick at My Chart, Privacy Preserving Visualization for Mobile Devices. This project was a collaborative effort with Professor Ma and Wang. Before diving into technical details, let me first introduce the overall background and motivation of this work. As you may know, data visualization is a powerful tool for data exploration and analysis. It enables people to better understand complex data sets and uncover valuable insights. With the explosive popularity of mobile devices, such as smartphone, tablet, these devices have become one of the major platforms for people to view visualization of various data, which often include sensitive personal information. That is particularly important as we increasingly rely on our mobile devices for manage our life. For example, people may check a bar chart on a healthcare application showing their health and fitness data, or a line chart showing their income revenue over time. This visualization often contains sensitive information that users may not want others to see. However, sensitive information shown in mobile data visualization can be easily leaked through shoulder surfing attack. The shoulder surfing attack arises when users view mobile data visualization in public areas, as other people nearby can also easily see the information displayed on the mobile phone. This can be particularly problematic when you are commuting or waiting in line at a coffee shop. Worsening the situation, prior research shows that only 7% of people are aware of shoulder surfing attacks when using their mobile devices. This means that when you are using your mobile devices, you are hardly aware that others are looking at the content on your mobile phone. This lack of awareness makes it even more crucial to develop ways to protect users' privacy. To solve this problem, we need to propose a method to prevent shoulder surfing attacks on mobile data visualization. However, there are some challenges that we need to address. To sum up this, preventing shoulder surfing attacks on mobile data visualization is challenged due to their glanceable nature of visualization. Additionally, it's hard to balance users' experience and privacy protection in mobile data visualization. So the specific question we address is how can we maintain visualization of visibility for user at proximity while effectively concealing from pickers at a distance? This question lies at the heart of our research and drives our research efforts. To address this question, we propose a privacy-preserving visualization technique that we will introduce in detail throughout the presentation. Our approach aims to strike the right balance between the usability and privacy protection. Our method transforms a regular visualization into one that is easily visible to the user while difficult for pickers to see. As shown in the figure, the user using the mobile phone can easily see the privacy-preserving bar chart, which is generated by our method. However, the picker who's next to the users cannot get a clear view of the mobile data visualizations. The key lies in adjusting the spatial frequency and luminance contrast of visual marks in a visualization, which make it difficult for pickers to discern the content of the visualization. The slides display the simulated result of our privacy-preserving visualization. As you can see, as the viewing distance increases, the visualization becomes increasingly difficult to discern. This is the desired effect, as it helps protect users' privacy while still allowing them to view their data. Our method proposes a masking scheme that can perform an original visualization into a privacy-preserving visualization. The masking scheme consists of two main modules, coarse-grained and fine-grained masking. The coarse-grained masking adjusts the original visualization in terms of its spatial frequency and luminance contrast. At the fine-grained level, we consider different characteristics of visual marks and propose customized masking schemes for them. Coarse-grained masking is inspired by the human vision system, that is, the ability of humans to identify objects from their background is jointly affected by the spatial frequency and luminance contrast. Firstly, spatial frequency refers to the frequency of color changes. When color changes more rapidly, the corresponding frequency is higher. We can visualize an image spatial frequency by converting from a spatial domain to a frequency domain. It's important to know that spatial frequency is not only determined by the image itself, but also depends on the human viewing distance. As a person moves farther from the image, the spatial frequency they perceive becomes higher. In addition to spatial frequency, humans' ability to distinguish objects depends on the luminance contrast between objects. Luminance contrast refers to the difference in brightness between two object colors. As the contrast decreases, it becomes harder for humans to identify bright and dark bars. To consider all these factors, research proposed a contrast-sensitive function, which is the black curve as shown in the figures. This is the black curve. And the contrast-sensitive function curve depicts the coupling effect between spatial frequency and luminance contrast on human vision perception. Normally, as the spatial frequency increases, humans need higher luminance between the darker and bright bar to distinguish them. As for the fine-grained level, we design different masking schemes for the different types of visualization marks, like rectangles, circles, and points. Visual marks are the basic units of a visualization, and they can be characterized into three types: the point, lines, and areas. We further categorize visual marks into line-based and area-based masks due to their difference in occupied areas, and design different masking schemes for different types of visualization marks. We design an area-based mask for area-based marks where the pixel at the center of the mask is retained and the other pixels are converted to the background color. The mask is tilted to cover the entire mark, resulting in area-based marks composed of discretized dots. The converted mark is then turned to high frequency. We import the CIE LAB color space when adjusting the luminance contrast of visualization instead of the RGB color space. The AL channel of the CIE LAB color space aligns well with the actual perception of luminance by the human vision system. By changing the luminance of the pixel of visual marks and background in the CIE LAB color space, we can accurately control the luminance contrast between visual marks and the background. For line-based marks, we design a different mask that takes into account the characteristic of line-based marks. This mask ensures that the continuity of the line-based mark is maintained, which is important for the readability of the visualization. Let's take a look at the example. Figure B shows the original line chart, and the figure C shows the line chart processed by the area-based mask. If we use the area-based mask, there exists discontinuity in the dashed right rectangles. However, if we use the line-based mask, the continuity of the line-based mark is maintained. This is crucial as it ensures that users can still understand the visualization while preventing shoulder surfing attacks. This continuity is essential because it allows users to quickly comprehend the visualization without needing to spend extra time guessing the trend of broken lines. We also apply the line-based marks on visualization axis and text because they are made of line bilatures. The figure in the slides also displays the difference between axis and text processed by the area-based mask and line-based mask. The text and axis in figure B is proposed by the area-based mask, as we can see in the red dashed rectangle. The text and axis cannot be identified clearly. However, in the figure C, text and axis are much clearer to human beings. We conduct two studies to comprehensively evaluate our method. In the preliminary user study, we invite 16 participants to evaluate different masking schemes and luminance contrast using a 5-point Likert scale. This helps us to narrow down the design space and identify specific combinations that ensure good visibility for users, as well as effective privacy protection for pickers. As shown in the list, the 1 to 5 represents the time and effort the participants need to identify the visual marks in the visualization. 1 indicates that they cannot see any visual mark in the visualization, while 4 means that they can see the visual marks in the visualization with additional time and effort. 5 means that users can see the visual marks at a glance. We select 4 popular visualization types for the study: bar chart, pie chart, scatter plot, and line chart. According to the rating results, we identify specific combinations that ensure good visibility for users, as well as effective privacy protection. Based on the preliminary study result, we conduct a user study to evaluate our method and recruit 18 participants. This study aims to assess the complete version of our approach with suitable variables in comparison to the baseline approach. The user study consists of quantitative evaluation and post-study interview. In the user study, we compare our method with 2 baseline methods: the original visualization without any processing and the cross-gram visualization processed by the cross-gram masking scheme. Based on our method, which process the visualization by both the cross-gram and fine-gram masking schemes, we conduct a within-subject study where the participants view the text visualization at 3 different distances: 30 centimeters, 60 centimeters, and 90 centimeters. This distance considers the representative daily mobile phone usage and shoulder surfing attack scenario. 30 centimeters denotes the distance between a mobile phone and users. 60 centimeters is the distance between a picker and the user's phone when the picker and user are sitting together. And 90 centimeters refers to the distance when the pickers sit behind the user in a public transportation like bus. Since visualization is composed of text, axis, and visual marks, if the participants can clearly identify both text and marks, they are able to comprehend the visualization. Therefore, there are 2 tasks for rating: visual mark visibility rating and text readability rating. Additionally, we utilize the same rating criteria as in the preliminary study. The figure shows the participants' average rating for each of the 3 methods and 3 different viewing distances. Figure A shows that when a normal mobile phone using distance, which is around 30 centimeters, participants can see the visual marks without any difficulties. However, when participants are 60 centimeters or 90 centimeters away from the mobile phone, their ability to see the visual mark in the visualization drops rapidly. Particularly at about 90 centimeters, they only perceive a small portion of visual marks in visualization. This indicates that our method successfully conceals visualizations from pickers while maintaining usability for the users. As for the text readability rating, Figure A verifies that participants can read the same content in the processed text as in the original text, because the average rating is slightly over 4 of the processed text, which means that the participants can clearly see all the processed text by our method. As shown in the figure B and C, participants had difficulty identifying the text once the viewing distance increased, resulting in a dramatic drop in their rating. Let's take a moment to discuss the qualitative feedback we received from participants regarding our privacy-preserving visualization techniques. Overall, the participants were happy with our approach, and we can summarize their feedback into 3 main categories. Information leakage concern. A majority of participants, 14 out of 18 participants, expressed concerns about the leakage of personal information displayed in mobile data visualization. Additionally, all participants appreciate the fact that our privacy-preserving visualization techniques effectively protect their privacy on mobile visualization when viewed from a distance. Also, most participants recognize the usefulness of the fine-grained schemes, which can greatly improve the visibility of process visualization. In general, the takeaway message is that shoulder surfing attack occurs when the picker is at a great distance from the user. By adjusting the spatial frequency and luminance contrast of visual marks in a visualization, our method can make pickers after a certain distance hardly see the privacy-preserving visualization. In the future, we plan to apply our method to more visualization types and mobile devices. Thanks you for listening to my presentation. I hope you now have a better understanding of our work on privacy-preserving visualization for mobile devices. If you have any question or would like to discuss further, please feel free to ask.